thought I would do a quick video here to demo the machine learning web app that we built to go along with the paper for the O'Shaughnessy Research Partners program. So this is what it looks like here. This is the website, RotoWorkshop.com. I went with that because roto is a prefix often associated with fantasy sports. And so a lot of the examples I'm going to use come from fantasy sports, so it seemed an apt name to use. So this is what the page looks like. On the left, there's a list of tables. Initially, there's no data. All of the data comes in the form of tables that we're going to typically get from a CSV file. That's what the app is set up to use. If you click on Add New Table, there's links to add in any of the data that I've provided for you automatically, or you can drag in your own files, your own CSV files. Pretty much any CSV should work. It just needs to have a header row that gives the name of each of the columns. So let's look at this one, drafted wide receivers. Okay, if you click on that, it loads it, and then it shows up here on the left. It says drafted wide receivers, and then it's highlighted, and then the data appears on the right. So this is data about a large set of receivers that were drafted in the NFL, and then I'm trying to predict from this data. What I'm interested in is this column that says success, which ones were ended up being successful in the NFL and according to some metric, and which ones did not. And I want to figure out how to predict that from the other information that I have. So this data column just shows you the data. You can click on any of these columns to sort by that. Click on it again to change the sort order. So you can see here that in the data set I have the fastest 40-yard dash times are 4.27 and 4.28, and the slowest of any drafted wide receivers over this time range were 4.81 and 4.80. If you click on the next tab over, plot, you can you can get some pictures of the data. Let me just focus on this scatter plot. So it's going to take from each row of the data, you have to pick out which column has the X value and which has the Y value, and it'll plot that in the picture. So let's say I want to do the X. I'll have that be the 40-yard dash, and Y be the final year receiving yards per game. So here's a picture of the data. At this point, it's pretty messy, although there does seem to be, it is a bit elongated, suggesting there is some kind of correlation between these two. If you want to get this is not so meaningful as it is, but if you add down below, you can tell it which column separates these examples into different classes. And in this case, the classes we have are those that are successful and those that are not. So if you click on this success column, if you click on the class column down here, choose success, it'll now draw in different colors those in the different classes. So now you can see from the picture that in general, the successful ones tended to have more receiving yards per game. There's not a lot of successes down there at the bottom. And broadly, it does seem to look like they have, there's quite a few that are slower, and they're not all clustered here on the left. So at least we can, just from the picture, we can tell that being slow is not necessarily relatively slow isn't I shouldn't say slow. These guys are all a million times faster than I am, but being relatively slow compared to the group doesn't necessarily mean you won't be successful. Okay, so you can choose any of the columns you want to plot, and that often will give you just useful information from looking at the pictures. But our main goal here is to build models. So when you want to build a model, you need to tell it you're trying to learn the model from data. You have to tell it which column of the data has the value that you want to learn. So in this case, the success column is the one that I want it to be able to figure out how to predict from the other columns. So I'll choose success. Then you choose which type of model that you want. There are four model types built in: linear and logistic regression, and then ensembles of decision stumps, either for regression or classification. But it can tell, since the success column only has two values in it, 0 and 1, it can tell that we want a classifier. So it's only going to suggest logistic regression or an ensemble of decision stumps. So let's do logistic regression first. It builds the model pretty quickly because this is a pretty small data set. And you can see on the left here, we end up with a new panel that shows models, and this one is a model that predicts success using logistic regression. On the right, you get a description of the model. It has information on how it did on the training set and how it did on the test set. So the training set is about 80% of the examples, and the rest, the 20%, roughly go into the test set. We can see that its error rate, the number that it classified correctly, was about 14% on the training set, but it jumped up to almost 24% on the test set. So maybe not surprising. It was trying to find a model that would fit the training set very well, and when we switched to the data that I hadn't seen, it didn't quite match that performance. It also gives a metric called pseudo R-squared. Let me not talk about that too much, but it tries to be an analog of R-squared for logistic regression. Although, let me just warn you, in general, these numbers are going to be smaller than what you'd see with linear regression. So 0.29 is actually quite a good pseudo R-squared, even though as an R-squared, it's maybe not, depending on context, maybe not fantastic. So below that, you see the parameters of the model. A logistic regression model has one parameter for each column of the data, and then also an intercept. And you can see how it makes its predictions. So it wants to see ages that are smaller. It wants to see heavier wide receivers. It actually does want faster wide receivers rather than slower ones, even though we saw in the data set didn't seem to have a preference for faster. Once you control for all these other columns, actually being faster does seem to be beneficial. It doesn't care at all about the vertical jump and so on. If you look at linear regression instead, there will also over here be a standard error estimate, so you can from that tell if these individual estimates, these individual parameters for the various columns are statistically significant or not, if that's something you want to do. Okay, so let's go back to the drafted wide receiver data, and I click on the Learn column, Learn tab, and I'm going to try to learn it again, and this time using an ensemble of decision stumps. So now it'll build that model. It takes slightly longer in this case. And now we can see the fit of that model. It has an error rate of about 10% on the training error, a little better than logistic regression. And then on the test set, it also sees an increase in error on the test set, not surprising. But its error rate is only 22.6%, which is a little bit of an improvement over what the logistic regression model had. So below that, for this type of model, this plot here shows you for each of the parameters what is the maximum weight that it puts on that parameter. Essentially what that means is what's the maximum probability that you can get just from looking at that one parameter. So the model looks at each parameter separately. From each one of them, it assigns assigns a probability of success, and then it adds those all up together. And if the total adds up to 0.5, then it's going to guess 0.5 or above. It's going to guess success. So you can get to almost 0.1 just from your weight, almost to 0.1 from your 40-yard dash. To get to 0.5, you'd still need to do to get some good scores from these other columns as well. So this is the maximum weight. That doesn't mean that every single example gets 0.095 as its probability. To see exactly which ones, what does your weight have to be to get that probability, get that amount added to your probability of success, click on the plot and we'll select weight. And so here is a plot that shows weight along the x-axis, and then here's how much it adds to the probability of success based on that value. So broadly, it's liking heavier wide receivers. In fact, these ones above 230 are the ones that get almost 0.1. It also gives some boost to those in the middle ranges. And this is an interesting case where there does seem to be a nonlinearity here. The receivers between 182.5 and 198.5, they do actually do better than in the data that we have. They do better than those between 198.5 and 209.5. And it's plausible that could be the case. I don't know. Maybe it has to do with cornerbacks' weights tend to maybe they're in this range, and ones that are a little heavier can beat them in contested catches, and the ones that are a little lighter can run away from them. And whereas when you match up to their weights a little better, it's easier for them to defend you. I mean, that's just speculation, but it's not hard usually to come up with reasons for why this might be real. But the data suggests that the data that we have at least suggests that this is the real shape of the relationship. Okay, let me look at one more. 40-yard dash time looks like this. And as we can see, just like in the the logistic regression, it does want faster wide receivers once you include all these other parameters. So those below, with the time below 4.459, they're the ones that get a almost 0.1 success probability. Although essentially, though, anything below 4.62, all of those actually have a pretty good score too. So it's not really that sensitive. It's only the really, really slow receivers, I guess, that don't get that probability added in. Okay, so there's a bunch of other features here. Let me quickly mention, you can click on, this is a model that has 100 trees in it, or at least it tries to get to 100 trees. It may not be able to get there because it stops being able to figure out how to improve it. But if you click on this, you can actually see what happens if you restrict your model to be smaller. So if you go down to just 5 trees, it actually focuses on just these 4 variables: career, market share, receiving yards. age, final year market share of touchdowns, and final year receiving yards per game. And we can go and if you click on career market share receiving yards, let me just show you this. This is when you have just the 100 trees, the final model. If you click on show all trees, then there's actually, it's showing you what the plot looks like for when you had just 5 trees, 10 trees, and so on. And they get darker in color. So the 100 trees is the darkest line, 80 is the next, and this very faint line here is what would it look like with just 5 trees. So with just 5 trees, it gives a huge bump, 0.25. So you're half the way to a successful prediction if you have more than 26.65% of the market share of the receiving yards on your team. Okay, and in fact, actually, interesting, looking above, this five tree model actually was the most accurate on the test data of any of them. So, excuse me, 10 trees is actually slightly better, but it doesn't necessarily get hugely better as you go along, and maybe there'd be a reason to use the 5 or 10 tree model instead. Okay, so last thing I want to do, I want to go to add new table. Once you have a model, you might want to use it to make predictions. That's the, you can look at the model and understand it just to see what it tells you about the data, but usually our goal in machine learning is to make predictions. So what I'm going to do is I'm going to go here, and instead of clicking on one of these links to import the data that I've provided, I'm going to grab some data that I have elsewhere. So here is 2017 NFL wide receivers. I can drag those in. And so this has all the same columns as before, but now it doesn't have a success column because I don't yet know if they're going to be successful. This success metric looks at 3 years of data, not just one. But here they are. Here are the drafted wide receivers from 2017. And now instead of the learn column, I'm going to click on the predict column. And it can tell that there are 2 models that based on the columns in the data, there are 2 models that would apply. And so I can say, let's say the logistic regression model, and it can say that it thinks Corey Davis is going to be successful, John Ross is going to be successful. That doesn't look great at the moment. Curtis Samuel, that looks good. It doesn't like Juju. That was a horrible mistake on its part. Cooper Kupp, definitely another mistake, and so on. So this is hard business. Kenny Galladay didn't pick. It's that doesn't look like a good set of choices there. Actually, let's go and see how this ensemble of decision stumps. It doesn't like very few at all. It doesn't like very many at all. It just likes Kenny Galladay. Well, at least it got that one right. I guess Isaiah Ford as well. I actually don't know anything about him. But Kenny Galladay, that was a good pick. I guess this one's a little more discriminating in what it sees. So in any case, you can build your models and you can apply them to your data set just like this. And hopefully that'll be useful for those of you, at least if you just want to play around with these ideas and bring in your own data and see if it gives you any useful predictions. If you run into any problems, I'm at Casey's Ad on Twitter and happy to chat about this or add new features that anybody thinks would be useful during my spare time. So just let me know. Thanks for watching.